But there is one more philosophy. We remove unwanted material, like in this case, if we remove unwanted material and we only left with this and all other material is unwanted material. If we remove unwanted material and getting the final shape, we call it as a machining. So now it uses the concept of what? Material removal, and that material removal is mostly in the form of chip that you can see in this diagram. So very simple schematic diagram is shown. So machining process essentially involves workpiece, then cutting tool. The cutting tool means the body which we are using to remove the material, and some fixtures are needed, some clamps, some tool post, some fixture arrangement that is needed. So essentially it involves three basic objects. Means only two, workpiece and cutting tool. The chip is anyhow it is removing from the workpiece. That is anyhow unwanted material. So conventionally there are many machining processes: turning, drilling, milling, shaping, grinding for specific application. But at the bottom line, the concept of material removal is same. That is a shearing process. Everything happening shearing, or in this context I can directly use synonymous for this, cutting. Shearing itself is a cutting. Even if you see a simple dictionary meaning of shearing without going in much engineering, you will find this word, cutting. Although shearing is one of the way to cut, there are many other ways in engineering. So shearing means basically some shear stresses are involved, and due to that shear stresses at certain plane, material is able to cut, and that is possible with the sharp edge or the harder body, and that we call it as a cutting tool. So essentially this cutting tool is conventionally we say 1.5 to 2 times harder than workpiece. So these are some fundamental requirements. We cannot cut conventionally, at least I am saying. There are many non-conventional machining operations. There we can use even softer tool to cut a harder material. But that is entirely different story. Conventional means when there is a physical contact of a cutting tool with the workpiece. We call it as a conventional machining, conventional processes, where your cutting tool should be harder than, at least 1.5 to 2 times harder than the workpiece. Then with this physical contact, shearing process happen and material will remove in the form of chip. So from modeling perspective, what one can understand, if we are modeling this process, I should have a workpiece, its dimension, its properties. At the same time, I should know the cutting tool dimensions, cutting tool materials, its geometry. And fixtures. What about fixtures? Fixture we will model in FEM as a boundary conditions. We need not to model fixture because we are not going to design fixture here. We are interested in machining operation. So basically fixture we will take care in terms of boundary condition. So all these three essential things I told you, right? Workpiece we need to model it, cutting tool we need to model it, fixtures will take care in boundary conditions. So now we'll try to move further, some more on machining. So why this slide is very important? As we started our discussion with orthogonal, but how to differentiate, or in reality I will tell you, all the processes I explained, turning, drilling, milling, they are essentially oblique machining. Orthogonal machining is just a simplification for research and engineering purpose. In reality, hardly there is any orthogonal cutting process. So how it is differentiated? In very basic definition by some of the books, they only rely on this angle. That is the angle between this angle. That is the angle between cutting edge and the cutting velocity vector. So basically the cutting edge is this, and the cutting velocity vector, it is shown by VC here. So conventionally in many books they simply say if the angle between the cutting edge and the cutting velocity vector is 90 degree, then we call it as orthogonal, otherwise oblique. But that is not a complete and true definition. So in many good books they also say this definition is a pseudo orthogonal. But the original and the more accurate definition is given by chip flow angle, theta. If this chip flow angle is 0, then we call it as orthogonal machining. And if that is non-zero, we call it as oblique machining. So due to this non-zero chip flow angle, cutting tool experiences all three components of forces, Fx, Fy, Fz, or in machining terminology it is called as cutting force Fc, feed force Ff, and radial force Fr. And if radial force is due to zero chip flow angle, it vanishes and our 3D components will simply convert into only two major components. One is called as cutting force, other is feed force. It is also called as thrust force. In machining terminology, it is called as thrust force, and Fc called as cutting force. So basically, if we are analyzing orthogonal machining, so only two components we need to analyze. So third component means basically dimensionality we are reducing from 3D to 2D. And one need to understand why this dimensionality is reducing. Means one of the strain component is getting 0 in orthogonal machining. Due to this zero chip flow angle, chip is not deviating at all. So the width of chip, this width of chip before and after cutting. So this is after cutting. This is the width after cutting. Let's say I am calling it as a W1 and this is W0. So this width is not changing at all. As chip is flowing exactly on the cutting face, there is no strain component acting in that direction. So this is essentially a plane strain operation or plane strain condition. This is another modeling aspect one should look at here. So although I am looking from theoretical background, but still as a modeling engineer, I got one very important theoretical concept that if I am modeling orthogonal machining, I need not to model it in 3D because anyhow in the third direction, that is the width direction, no strain will be there. So I can simply model like workpiece in 2D, something like that, and this is cutting tool. So width direction is perpendicular to the screen. We need not to model it because anyhow in that direction no strain will be developed, and the whole process I am simplifying it as a plane strain analysis. So when I will explain this in meshing, we will again highlight this point. One should use plane strain element to model orthogonal machining. Okay, and for 3D, if oblique machining is there, we can directly go for 3D elements, 3D stress element. But if I am modeling orthogonal machining, that is essentially a plane strain analysis, and one should use plane strain element for it.